Okay, Unit 7 is going to open with a pretty strong set of review problems. These are all things we covered before break. So first of all, simplifying radicals is a matter of looking for those perfect squares by breaking it down into its factors. We don't have to go all the way down to perfect squares. We just need to get down to perfect squares or prime numbers that we can then regroup, like those two, as 2 squared times 4 times 7. Squaring and square rooting are opposite operations. So the square root of 2 squared is 2. The square root of 4 is also 2. And when I pull the numbers out and they become coefficients, they get multiplied. The square root of 7 cannot be simplified, and so I have 4 square roots of 7 as my final answer. Now 45 has a perfect square of 9. When I pull that out and take the square root, I end up with 5 times 3 with a square root of 5 left over, and so I have 15 square roots of 5. When I have a fraction, I can go ahead and simplify within the fraction first as long as there's no addition or subtraction. 24 and 80 have a common factor of 8. Now remember, I cannot leave a radical in the denominator, so I need to rationalize this denominator by multiplying by radical 10 over radical 10. Remember, that number there is really 1, so I'm not changing my problem. Numerator times numerator is 30. Radical 10 times radical 10 is 10. If you need to think about it as the square root of 100, if you need to think about it as radical 10 squared, regardless, it becomes 10. Now in this next example, we also have radicals under with a fraction bar. Since there's no addition or subtraction, I can go ahead and simplify first. So the square root of 8 over 2. 8 is not in lowest terms. I can rewrite that as 4 times 2, which becomes 2 square roots of 2 over 2. The 2's cancel, and I have the square root of 2. E snuck on there and is a problem we don't know how to do yet. Now, operations with radicals, again, a review concept. Remember, they behave just like variables. So if you could add 1x plus 4x, we can go ahead and add 1 radical 5 plus 4 radical 5 to get 5 radical 5. We could not add 2x minus y, and so there is no way we can add or subtract or simplify that expression right there. Now C appears at first glance that we can't simplify, but if you look closer at 63, 63 is really 9 times 7. 9 is a perfect square, so when I simplify this, it becomes 3 radical 7. Now my radicals are exactly the same, and I can add them for 8 radical 7. Now multiplication is easier than addition and subtraction, because remember we just combine them all under one radical. Instead of multiplying 6 times 8, I'm going to go ahead and write this as 6 times 3, because your 18 is still right there, but by doing this I see 6 times 6, which is a perfect square. Take care of that, and it leaves 6 radical 3. In the same way that k cubed can be rewritten as k squared times k. Square root of k squared is k. Square root of k is your leftover. Again, in this one, I would simplify the radicals first. 27 and 48 have a common factor of 3. And when you do that, you end up with 4 square roots of 9 over square root of 16. Those are nice, perfect squares for me. And when I do that, I see that these cancel, and I'm left with 3 as my answer. Now, rationalizing the denominator is that good math grammar that we talked about before break. And remember, we can't leave this radical 2 in the bottom. So I'm going to multiply by 1. And how I frame my 1 is so that I can make a perfect square in the bottom. Numerator becomes the square root of 2. Square root of 2 times the square root of 2 is 2. There's no simplifying that can be done, and that is my answer. Now remember, if you want to think about this as the square root of 4, which then becomes 2, that's perfectly fine. In B, my denominator is the square root of 3, so I'm going to multiply top and bottom by the square root of 3. That gives me 5 square roots of 3 over 3. I can't simplify, so that is my final answer. In C, my denominator is the square root of 5. So I'm going to multiply top and bottom by square root of 5. Remember, radical times radical, so I have 3 radical 10 all over 5. I can't simplify 3 and 5, and so that is it. It's tempting to want to simplify the square root of 10 and 5, but remember that square root sign changes it. That's a number that is not, does not have a factor with 5. Now in this one, I'm going to go ahead and simplify the rational or the radicals first because there's no addition or no addition or subtraction, excuse me. And when I do that cancel, it leaves 2 radical 2 because I canceled the 3 over 3, and my problem is done. Those problems all represent a quick review of skills that we practiced before break in the last unit. Now, the Pythagorean Theorem is also an old review skill. I always draw a line from the right angle to the hypotenuse to help myself be sure to get everything in its right place. A couple of notes here. The hypotenuse is always the longest side. That helps you do a quick check if your answer is appropriate or not. And a big caution goes up here. And that big caution is that the Pythagorean theorem only works with right triangles. Do not try to apply the Pythagorean theorem to non-right triangles. It will not work. Now, after we've been practicing our radicals, it's easy to see how we are going to be expecting answers to be in exact form, which means no decimals, using your skills of simplifying radicals to leave answers in their exact form. So what do we have here? We have a pretty straightforward problem where I have 10 squared is equal to 6 squared plus b squared. So I have 100 is equal to 36 plus b squared. 64 is equal to b squared. I undo the square by taking the square root. B is 8. I don't have to consider -8 as an answer because I'm dealing with lengths. In this next example, I'm missing the hypotenuse, so I'm going to have c squared is equal to 5 squared plus 12 squared. C squared is equal to 25 plus 144. C squared is equal to 169. Square root both sides, and C is 13. A couple of very straightforward applications of the Pythagorean theorem. But sometimes they're not so straightforward. So in number 3, I actually have an isosceles triangle because those are equal. And when I have that perpendicular segment, I know that that bisects this side. So I know that this side right here is 4. The triangle I'm going to be looking at is right here. And so I'm actually going to be solving for that side right there with the equation of 5 squared, that's my right angle, is equal to 4 squared plus b squared. 25 is equal to 16 plus b squared. 9 is equal to b squared, and b is 3. This one is going to be our first taste of a non-nice, neat, tidy integer answer. So I have 12 squared is equal to x squared plus 8 squared. So I have 144 is equal to x squared plus 64. Subtract 64 from both sides. Now when I take the square root, I'm left with a non-perfect square. So now I'm back to my factoring skills. I know that 4 goes in here 20 times, and I know that 4 goes in there 5 times. So I could rewrite 80 as 4 times 4 times 5, which means that I can simplify x is the square root of 4 is 2, the square root of 4 is 2, the square root of 5 is left over, and I'm left with 4 square roots of 5. That is my exact answer, and much preferable to a calculator. A couple of word problems. The foot of a ladder is placed 6 feet from a wall. If the top of the ladder rests 8 feet up on the wall, how long is the ladder? Well, we are assuming that all of our buildings are nice and square with the world. And so that means that they're all going to intersect at a 90-degree with the ground. If the foot of the ladder is 6 feet from the wall, that means this measure right now is 6. If the top of the ladder rests 8 feet up on the wall, that means this is 8. And this, which happens to be our hypotenuse, is the length of the ladder that we are after. So this is a quick Pythagorean theorem problem. Once I see my picture and the way my numbers work together, and I find out that my ladder is 10 feet long. Now this next example is kind of fun and a little tricky. In the Old West, settlers often fashioned tents out of a piece of cloth thrown over tent poles and then secured to the ground with stakes, forming an isosceles triangle. How long would the cloth have to be so that the opening of the tent was 4 meters high and 3 meters wide? Well, what we're talking about picture-wise is something along these lines, where we hope that our tent pole in the middle is straight up and down. Now, if the opening of the tent is 4 meters high, that would be this length, and from here to here in the opening is going to be 3. We've already discussed how that perpendicular bisector works, and that is going to make each one of those sides 1.5. We're going to focus initially on this half hint of the triangle. Again, we're going to solve for the hypotenuse. So c squared is equal to 4 squared plus 1.5 squared. C squared is equal to 16 plus 2.25. C squared is equal to 18.25. Now, we don't measure length in terms of square roots, so this is a time when it is appropriate to use your calculator and come up with an approximate. And so C is going to be about 4.3 meters. But that's where the trick comes in, because we really don't want C. We want how long the cloth would have to be. So we really need to know this whole distance, and since it's isosceles, this is C, and so the actual length we're after is 2 times 4.3